Hello everyone, my name's Dr. Vile, welcome to my YouTube channel. The purpose of this channel is all about getting you ready for your A-level chemistry exams, and with this in mind, this video is going to focus on organic functional group testing. So for instance, how do you test for an aldehyde, how do you test for a ketone, how do you test for a carboxylic acid, and so on. If you find the video helpful, please remember to like it, please subscribe, please keep checking back for more content. Okay, so we're going to look at how we can distinguish firstly between alkenes and benzene. Now hopefully you remember back to AS chemistry, the test for an alkene, and you add bromine water, and what would happen is the alkene would decolorize the bromine water. So you'd go from, say, orange to colourless. And if you did the same thing for benzene, you'd get no reaction. Benzene is not reactive enough to react with bromine water. So this is a really good test if you had to distinguish between a benzene compound and an alkene. The alkene will decolorize the bromine water from orange to colourless, whereas benzene gets no reaction. So you'd just be left with that orange solution. Okay, the second test I've got here is oxidation using acidified potassium dichromate. So when you take certain functional groups and you warm them with acidified potassium dichromate, the colour change that you see goes from orange to green. And what's going on is that in potassium dichromate you've got the K2 Cr2O7 and the chromium is in the +6 oxidation state, and when it oxidizes something else it gets reduced in the process, so the chromium gets reduced to +3, hence why you see this orange to green color change. So what functional groups would this work with? Well, basically anything that can be oxidized. So you could work this with a primary alcohol. That would give a positive test with this. A secondary alcohol would as well. It would get oxidized to a ketone. And you could do it for an aldehyde as well. And these would all give this orange to green colour change. But what we could do is rule out, for instance, a ketone, because a ketone is already fully oxidized, can't be oxidized further. You could rule out a carboxylic acid. That would already be fully oxidized. You could rule out a tertiary alcohol as well. Tertiary alcohols are, it's impossible to oxidize a tertiary alcohol. Phenol is one compound we need to be able to test for. Remember, phenol is a benzene ring with an OH group on it. And what happens with phenol is it's far more reactive than benzene. And the reason it's more reactive is the oxygen's lone pair of electrons almost become part of the benzene ring. They push the electrons into the benzene ring, making the pi cloud more negative, and therefore it's far more able to react with an electrophile. So if you react phenol with bromine water, you'd actually need 3 equivalents. That is a 3 there, that is a dreadful 3. 3 equivalents of the bromine water. Then what happens is we get substitution, and we substitute in the 2, the 4 and the 6 position to give 2,4,6 tribromophenol. In terms of what you would see 2 things that you need to know for this test. The first one is that you get a white precipitate, and that's because of the 2,4,6 tribromophenol. And also you would see decolorization of the bromine water. So the aqueous bromine goes from orange to colourless, because it's being reacted with the phenol. To balance this equation, because this is not balanced yet, the byproduct from it is hydrogen bromide. And you'd need 3 equivalents of the HBr to balance it. The second test for a phenol is to add aqueous iron chloride, and you get a violet solution produced. And the reason that this happens is that the iron binds to the phenol, and the phenol actually acts like a ligand. And what it does is it splits the d orbitals into the 3 lower in energy and the 2 higher in energy, so you get the D to D transition, so it becomes a coloured complex. So second test for a phenol is to add aqueous iron chloride, and you get a violet solution produced. In the carboxylic acid booklet, you need to know about the relative acidity of carboxylic acids, phenols and alcohols. So firstly, we need to know the order. So carboxylic acids would be the most, so let's call that number 1. Then phenol would be the next most acidic. And alcohols would be not acidic, really. They're basically neutral. And we looked in the notes about the reasons for that. So with the carboxylic acids, what you get is you've got this carboxylic acid group that loses the hydrogen, because it's an acid, to form this CO2 minus. And this minus charge gets spread across both the oxygens. So what you end up with is the carboxylate ion, where the negative charge is kind of spread across both the oxygens. And therefore, because this is really stable, it's more willing to lose its H+ ion, making it a slightly stronger acid. Phenol forms the phenoxide ion, and the p orbital on the oxygen kind of gets incorporated into the pi cloud of the benzene ring, making this a pretty stable ion. So phenol is quite willing to lose that hydrogen, making it relatively acidic, not as acidic as the carboxylic acid. And with an alcohol, there's nothing to stabilise the negative ion, so it doesn't form. So we need to be able to propose a test that would enable us to therefore distinguish between carboxylic acids and phenols based on this information. So phenols and carboxylic acids, these will both react with sodium hydroxide, which is a strong base. However, if you add sodium carbonate, sodium carbonate is an example of a weak base. So the sodium carbonate will only react with the carboxylic acid. So if you have a carboxylic acid and a phenol, you'd add sodium carbonate and you'd only get a reaction with the carboxylic acid. And what you would see is fizzing due to the CO2 produced. And of course you could bubble that through lime water, which would go milky if you wanted to confirm it was CO2. And the alcohols wouldn't give an observable reaction even with the sodium hydroxide. Okay, so we can use especially the sodium carbonate to distinguish between a carboxylic acid and a phenol based on the strength of the acid. Okay, next one is distinguishing between aldehydes and ketones. Might just be worth drawing those. An aldehyde has a C double bond O at the end of a chain, whereas a ketone has a C double bond O in the middle of the chain. Now there are 2 reagents you can use. Let's firstly treat it with Tollens reagent. I'm not going to go into the chemistry in much detail of what happens here, but you'll get a silver mirror with the aldehyde and no reaction or no observable reaction for the ketone. And the reason is Tollens reagent has this silver 1+ ion. And what it does is it's able to oxidize the aldehyde through to the carboxylic acid, and the silver ion gets reduced to form silver, which is why you get a silver mirror. Ketones can't be oxidized any further. So that's the first one. We can use Tollens reagent. The second one is we can use Fehling's reagent. Now Fehling's reagent has the copper 1 plus ion, and it works in a pretty similar way. Or is it copper 2 plus? It's copper 2 plus. It's copper 2 plus. And the copper 2 plus gets reduced to copper 1 plus, and that causes the aldehyde to get oxidized. So what you'd see for the aldehyde is kind of a reddy brown precipitate, and no reaction for the ketone, for the same reason that the ketone can't be oxidized any further. Okay, so Tollens or Fehling's are both acceptable for that. You do need to know both though, because they might say a particular compound was treated with Fehling's. What would you expect to see? Okay, the haloform test for methyl ketones. Just to clarify what we mean by a methyl ketone, something like propanone is an example of a methyl ketone because there's a methyl group next to the ketone group. It's exactly what it says on the tin. Whereas something like pentanthreone, just as an example, has CH2 groups next to the ketone group. So this will work, propanone will work, this will not work. And to do this we need sodium hydroxide and iodine. And what you get when you treat a methyl ketone with sodium hydroxide and iodine is you form CHI3, which is liberated, which is a yellow-orange precipitate, or a yellow precipitate. Let's go with that. This does not just work for methyl ketones, it will work for alcohols, which when they're oxidized become methyl ketones. So for instance, just to give one very quick example, if you had propan-2ol, if you oxidize propan-2ol, you form propanone, and therefore this will give a positive test for this as well, because when it's oxidized, which will happen under these conditions, you'll form a methyl ketone, and therefore it gives a positive result. And the precipitate is this CHI3, and that's basically where the hydrogens of the methyl group that are bonded next to the ketone swap for iodines till eventually you get this CHI3 that breaks away from the molecule, which is what the precipitate is. Okay, so it's a test for methyl ketones and alcohols that could be oxidized to methyl ketones. And then lastly, 2,4-dinitrophenylhydrazine, 2,4-DNPH, as you might see it somewhere. This is a test for a carbonyl compound, so it'll actually give a precipitate for aldehydes and ketones. So that's the two groups that we're looking for here with 2,4-DNPH. The colour of the precipitate does change depending on the structure. Normally a kind of orangey red type precipitate. And it will give a positive result for an aldehyde and a ketone. But where this is quite a useful technique is that you filter the precipitate. Do you remember this one, where you can filter the precipitate, dry it off, and then measure the melting point of the precipitate. And the melting point of the precipitate will tell you which compound you had to start with, because you can look it up in a database. So you add 2,4-DNPH, get this orangey yellow precipitate. The colour does vary slightly. and then you filter off the precipitate and measure the melting point. But if it gave a positive result for an aldehyde and a ketone, at this point you probably get the tolerance out and try and work out which one's which, if you were trying to distinguish between two of them. Well, thank you for taking the time to watch this video. If you found it helpful, please remember to like, subscribe, share with your friends, keep checking back for more content, and I'll see you next time.